So this morning we looked at searching. This afternoon we're going to get a bit more advanced and look at pattern matching. The two are actually quite closely related, as you'll see. So pattern matching. In the examples we saw this morning, we described two methods that can be used to search for a key. Sometimes we want to search for something more complex than a single number. That is what we might want to search for a pattern. For example, what if we want to check if the string Java is contained in the sentence, Jack said that Java is fun. In this case, we need to check if there is a sequence of characters contained in the sentence that have the letters J, A, V, A in that correct order. So it's a bit different to just searching for the one character we saw earlier, but as you can see, they're very related problems. On the next few slides, we'll describe a few methods that can be used for such pattern matching operations. The first is the brute force algorithm. In some ways, it's the most obvious algorithm. It's the one you probably come to first. The brute force algorithm compares every single character in the pattern with the sentence until a match is found. Here's a visual of how that's done. So, for example, it starts with the J's and says, oh, that's matched, that's great. And then goes to A's, sees they're matched, great. And then it sees C and the V don't match. So then it tries the next position and sees if Java matches there. Well, it's an A and a J, so it doesn't match, and it carries on through. So as you can see, that Java carries on through trying to match at every single position and continues index by index until either it's the end of the text, or in this case, until the pattern is actually found. The brute force algorithm performs comparisons of every character in the text until a match is found. In the worst case scenario, the brute force algorithm compares every character in the text with every character in the pattern. That results in a comparison equal to the length of the text multiplied by the length of the pattern. And thus in big O notation is big O n times n, where n is the length of the text and m is the length of the pattern. So it really can take a long time to process and to work through a string like this. You'll be glad to know there is a better way to do it. We're going to talk today about the Boyle-Moore algorithm. In fact, we're going to talk about a slightly modified version of the Boyle-Moore algorithm. Because what we're going to talk about is one of the heuristics the Boyle-Moore algorithm uses. There is another heuristics, which is called the good suffix rule. We're not going to discuss that at this stage, just due to its complexity and the fact it's far beyond what a first year should have to know. So we're just going to talk about a modified version of this algorithm. The way the Boyle-Moore algorithm really improves in the brute force algorithm is by applying some heuristics. So the heuristic we're going to look at compares the end of the pattern rather than at the beginning. That is, they perform they perform from right to left in the pattern rather than from left to right. So they start at the end of the pattern rather than the beginning. That's what I'm trying to say. Great. If a mismatch is detected, we search the pattern to the left to see if the mismatched character exists in the pattern. If it does, you shift the pattern until that character is aligned in both the pattern and the text. If there is no such character to the left of the pattern, the shift requires that the pattern past the character and continues. This is referred to as the bad character rule, and I'll be honest, it makes very little sense when I'm saying it in English, so we're really going to have to see an example to see how this works, and it's a lot easier than it sounds, I promise. So, I said we do a right to left comparison. We start at the end of our pattern we're trying to find. We note that the A in Java does not line up with the K of Jack. Okay, so we're starting at the end of our pattern, so that's the A, the last letter in Java is the A. Then we say, okay, that doesn't work, so we need to do some mismatch handling. Then we say, does the K appear to the left of the pattern after the A? So if we look through GAFA, is there any K in it? There's not. So we know that we can move the pattern completely past the K and continue with the search operation. So we actually move it completely past the K, got nothing to do with it, and it goes to the I instead, which then again we try and match with the A in Java. Again, we notice the I and the A don't match. We look through Java and note that there's no I in there in our pattern we're trying to match. So again, we can move it 4 places on, and we carry on doing that until we find the word Java. In deciding how much shift to apply when a character mismatch occurs, we first have to really process the pattern that we're looking for. Processing the pattern does add to the computation time. Therefore, depending on the size of the pattern you're looking for and the size of the text, the brute force algorithm can sometimes run faster than the bar-and-rule algorithm. However, the benefits show up when we are searching for a single pattern in many different texts, as this means that we only have to process the pattern once. It also shows up if it's a very short pattern you're trying to look for in a very long text. There are several ways to process the pattern, one of which includes the use of a two-dimensional table. Cheese example, which I'm going to give you here, uses a map to check for the presence of bad character and a list of integers to store or shift information. The performance of the bar-and-rule algorithm, and remember we've not quite seen the full bar-and-rule algorithm, we've just seen one of the heuristics. But the performance of the full algorithm depends on how quickly we can decide how much to shift the pattern. The faster that process is, the faster the algorithm can run. Interestingly, it actually has a worst case performance of O n times n, assuming we can complete the shift in a constant time, which is the same as a brute force algorithm. However, in reality, that is far less likely to happen. In some cases, the bar-and-rule algorithm can actually skip really large portions of the text. Remember, the amount it skips is proportional to how big the pattern is you're looking for. So, we've got searching algorithms. We've got linear search and binary search, which is looking for one character or one integer in a pattern. Then we've got fractal pattern matching, the brute force pattern matching, the bar-and-rule pattern matching. And you could actually use hash tables, which we talked about a number of weeks ago. I'm going to leave that for you to investigate. What I'd like to do at this point is to stop the video, it's almost finished anyway, and talk through each of these 5 different algorithms. What do you think the comparisons are? Where would you tend to use each one, and why would that be the case? I'm going to leave you to talk that through. Hope you have a really good day. Good luck with the work-based learning coming up, and that is the end of the software engineering. Take care.